Welcome back. In the previous videos, we learned how free radical mechanism occurs and what are the possible products with respect to primary, secondary, and tertiary carbons, right? And we also looked at the stability of those products, and we determined which one would be a more stable product over the other. All right, and for today, we are going to look into how an alkene, it could be any alkene, when it reacts with halogen, like a chlorine or bromine, what kind of reactions happen there. All right, now before we get started, I do want to point out a couple of foundational things, okay, that probably would carry over for the remainder of the courses that you may take in organic chemistry. Okay, so it's very important you understand. Let's, for time being, let's just say we have A connected to B. Okay, the reason I'm using just letters instead of any particular element is just to keep it very general, because this concept is generalized across various areas, and it's very important you understand the concept, then get occupied with, oh, should it be carbon, should it be nitrogen, things like that. All right, let's say you have two elements that are connected by a double bond. Okay, now we all know that a double bond or any bond is made up of two electrons, right? So in the free radical, we suggested how one electron gets combined with something else and you're left with an odd electron, right? So whenever you're dealing with free radical, the issue of positive or negative does not become your concern. Whereas when you move a whole bond, then you do have to determine that whether something is positive or negative is very much critical. All right. Now, if you refresh your brain from your general chem classes, you do realize when electrons are lost, okay, I'm saying this in bracket, electrons are lost, okay, the element typically gains a positive charge. And if electrons are gained, then the element typically gains a negative charge, right? So the moving of bond is very important in organic chemistry, because down the road, we will learn a concept called resonance, okay, which I don't want to get into now, but I'm preparing you up for that. And then in the successive videos, in this part of the content, we will learn Diels-Alder reaction, okay? And moving a bond is a must, all right? So let's say if this bond were to move, okay? And you can only move a bond to one adjacent spot or to the immediate element, okay? So if that's the case, if I move this bond into here, okay, the whole bond is moving, okay? When you mean like this, the way I've drawn it, it means you're moving the whole bond, all right? And what is the consequence of such an action is the bond that connects A and B stays the same, but it's just a double bond. I'm going to draw it in a different color. Because the tail of this bond, okay, is more closer to this element, and the head of this arrow is more closer to the element, what it really implies is this bond that contains two electrons is completely transferred from this element to this element. It's like a bank transaction, okay? If you want to give somebody, you want to donate $10 to a charitable organization and they want to take $10 out of your bank, well, your bank statement would reflect a negative $10, and the people you donated the money would reflect plus $10, right? Same deal here, right? But again, if you take the bank analogy, you got to flip the sign, because we're in a chemistry class, okay? Because everything in chemistry is just opposite to how you encounter things in regular life, right? So if you apply that, then A is lost both its electrons, okay, and B has gained both electrons. Now you don't need to say this, you can simply say negative. It implies that both these electrons have now been given to B. Now with the bank analogy in a normal life, the A would be, you know, negative, B would be positive, right? But you got to flip the sign, because in chemistry, I think the confusion happens primarily because of electron being negative, okay? So this is important you understand this, okay? Because if you don't understand this, then we will have some problems that we may have to fix to help you understand this concept, okay? Keeping that in mind, okay, whenever a bond, or for that matter, a pair of electrons is lost, the element that loses that pair of electrons gets a positive charge, and the element that gains the pair of electrons gets a negative charge. With that in mind, let's go further into the first reaction we're going to do, where we are going to take, say, some alkene, okay? This is, if you all refresh your memory of naming that we spend considerable amount of time, this would be 1-propene, right? If this reacts with Br2, okay, what are the products? Is there more products, or is just only one product? We're going to figure it out. All right. So again, this is something probably taught to you in a general chemistry class, okay, which is Br. It's got these 2 electrons, but it also has these additional electrons on the bromine atom. Now you don't need to, you know, go back and relearn the whole concept, but if you can just remember this much, that's good enough. Again, as we go more and more, we may not write these outer electrons, because again, this is just written the first time around to help you see what's really happening. Okay. So I am going to redraw this molecule, plus I am going to draw it this way, at least for the first example, but you know, over the course of time, it's not so much of a concern. Okay, so what's really happening here is you have the double bond, right? Right? The double bond makes a bond between the Br and, well, it's important. Again, there's 2 things I do want to point out is, whenever you lose a bond, you're not attaching it here, you're attaching it, okay? So let me draw the mechanism and maybe explain it again, okay? You're using this bond to connect this carbon right here to the Br, and one of the electron pair, the whole pair, gets transferred here, okay? Essentially, bonds can also make a bond, like a bridge, okay? So what really has happened is, actually, let me retain my red so it makes more sense to just have what has happened in blue. So what has really happened here is, so you connect, and in the process, what happens here is this, let me get my blue back. Because this is connected, this gets detached, okay? I just told you, whenever a bond is fully moved, wherever the head faces gets the negative, wherever the tail faces, the element close to it gets a positive charge, right? So what really has happened here is this Br, this bond right here is used as a bridge to connect this carbon to the Br, and this pair of electrons, keep in mind, to make a bond, you need a pair of electrons. So this pair of electron on the bromine is used to connect the Br to this carbon right here. Okay, now going back to the same thing, because this bond, right, is not really lost, it's used as a connectivity, you cannot put a positive charge here. Whereas here, the electron is lost from the bromine. It's only when the electron is lost completely you give positive or negative. Here it's just a matter of this bond is lost, but it's not really given to the bromine. It's used as a bridge to share, which is why you don't see a positive charge. Whereas here, the bromines clearly lost a pair of electrons. So that gets a positive charge. Okay. Now, here, the same deal. Plus Br. Now, if you see, the bond is being transferred to the bromine as a pair of electrons, right? So that means you have to write it as a negative charge, right? Now, this is very, very important. This is called a bromonium ion. Okay, you don't need to, I'm not sure if they will test these type of things, but it's always good to have that knowledge. This is called a bromonium ion. Now, what happens is, as I said, anything with positive charge or radical is sort of a intermediate, means it's kind of unstable and it wants to get to some kind of stable form. So here's what's going to happen. So the Br minus, okay, will attack this carbon right here, moving this bond back on to here. Now, if you keep in mind, let's write this actually so I can explain it further. Okay. Okay, so now this Br is here and this bond is now moved here, means it's disconnected. Okay, so the Br is now by itself. Okay, now we have two Brs, but because this had a positive charge, a bond is also equal to a negative charge. A bond is also equal to a negative charge in chemistry. If you haven't learned that in your general chemistry class, then it's high time you learn it. A bond is technically equivalent to one negative charge. So a negative charge is transferred to the Br. There's also already a positive charge, so they cancel out, and that's your product right there. I'm not going to put it in bracket. I'm just going to box it. Okay, we can do, you know, thousands of reactions on this kind, but what is really important is that you understand the movement of arrows. You don't just want to put them anywhere you like. Okay, there are specific reasons why I drew each of those arrows in different colors so you can see the transformation on what's happening. But what is more important is the positive and the negative. Okay, let's say you go through this whole reaction and you didn't write the positive charge. That does not count as correct answer. So is the negative. Okay, so you cannot just randomly move arrows, or you cannot randomly give some positive charge or negative charge, or you can just put the positive charge anywhere on the molecule. It still means you got the answer wrong. Okay, so it's really important that you drive through a process. So let's just look at one more example on this so that you kind of get the idea. But if you see this time, I'm just not going to write all the extra electrons, just keep it simple. So okay, so this is the double bond plus Br2. You can use Cl2, you can use I2, you can use F2, so your choice, but I'm using Br2 here. You can use Cl2. So what first happens is, this is the reaction. So I'm going to rewrite the molecule plus Br, and I'm going to write it this way. As I said, for convenience, I'm just not writing the lone pair of electrons on the Br itself. So what happens? The bond, or actually if you want, let's put it there. Okay, so the bond is used as a bridge to connect this carbon right here to the Br and any one of the pair of electrons. It doesn't have to be this, it doesn't have to be this, this doesn't have to be this. They're all equally the same. And this pair of electron is used to connect this. You cannot connect it here. I have seen students do that just out of impulse, They just want to connect the loose ends, and that's not how it works. This is where the bond is taken, so you can only connect these two carbons. You cannot connect this. So what's the product? I mean, what's the intermediate? So you have this, rewrite everything, okay? And then this is where the Br is going to be connected. And the Br gets the positive charge because this, and then in the process, let me get, I forgot one more arrow. This goes out. So you also have a plus Br minus, right? Now the Br minus attacks this side and this moves in, right? Again, like I said, a bond is equal to one negative charge. So a negative charge and a positive charge cancels out, which leaves us with, this is the first Br that was originally there. And I'm going to write this Br in a different color. And this is called a anti-addition. Okay. What is an anti-addition? It's very similar to the trans concepts we have learned. Since addition is attacking from the same side, anti-addition is attacking from the opposite side of where the Br is. This is definitely the opposite, so it's called an anti-addition. And this is how you add halogens, like a diatomic molecule, like a bromine, to an alkene. Okay, so this is very important. Now, the reason I brought this example is, if you remember, when we did our limonene synthesis and we made our orange oil, obviously I didn't give you a bromine water, but this time I'm going to give you bromine water, but I didn't give you permanganate solution. And you added a little bit of that to the oil, and the the potassium permanganate color got decolorized, right? We will learn that reaction also. But this week in lab, you've prepared clove oil, okay, eugenol. Eugenol's got a double bond, and when you add this bromine to it, you would see what happens, okay? So this is precisely the reason why I'm teaching this particular reaction. Is this is exactly what will happen in your eugenol when you add your bromine water to your eugenol. The double bond would go through this sequence of reaction, and that's what would decolorize your bromine water. Bromine water is kind of really reddish brown color liquid, and that color would fade away, which indicates the presence of a double bond. Okay, so this is of importance. Okay, so if you want to be absolutely sure that you have in fact made pure eugenol, only way you can test it is add bromine water. And then if the color of the bromine water gets faded away, then you know that you have made good quality eugenol, right? So this reaction has a practical application on, so if someone made some kind of oil and that has unsaturation in it, and they want to know if it is in fact unsaturated or not, then this is one way to test unsaturation in a compound. Unsaturation refers to presence of a double bond. All right, so when I come back next, I'm going to walk you through Markovnikov and anti-Markovnikov addition reactions. All right, so stay tuned.